Hello Stat 200, welcome to the full video lecture on confidence intervals. The content covered here is covered in Chapter 3 of the Lock 5 textbook. The full video lectures can get long, so I recommend that you take breaks in the middle of this video to look through the online notes or textbook, or to work through a few examples on your own. These are the learning objectives that we're going to be covering. At the end of this lesson, students should be able to construct and interpret a sampling distribution using StatKey, interpret confidence intervals, explain the process of bootstrapping, construct bootstrap confidence intervals using StatKey, and construct bootstrap confidence intervals using Minitab Express. These 5 learning objectives are going to serve as an outline for this video. But first, let's review the population parameters and sample statistics that you're going to see this week. Population parameters are fixed values, but we rarely know them because it is often difficult to obtain measures from the entire population. Statistics are known values computed from a sample. They are random variables because they differ from sample to sample. You might remember in the first 2 lessons, you learned how to take simple random samples using Minitab Express. Every time you took a simple random sample from the same population, different cases appeared in each sample. You may have computed a sample statistic, such as a sample mean or sample proportion, for different simple random samples from the same population, and you should have found that those sample statistics were different in each sample. This is what we mean when we say that sample statistics are random variables. It's because they're different or they vary between samples. Let's start with the first learning objective. Construct and interpret a sampling distribution using StatKey. This is covered in section 3.1 of the Lock 5 textbook. We just saw that sample statistics are random variables because they vary from sample to sample. Sample statistics have a distribution called the sampling distribution. So if we would repeatedly take simple random samples from the same population and record the sample mean or the sample proportion, we could construct a dot plot or a histogram of all of those sample statistics, and that distribution is known as the sampling distribution. Let's go to StatKey now to look at an example. In StatKey, in the sampling distributions row, you can see that there are 2 options. We can construct a sampling distribution for a mean or a sampling distribution for a proportion. Let's start by looking at an example for a sampling distribution for a proportion. In StatKey, there are a few data sets that are built in. For proportions, we also have the option of editing the proportion. You can enter any population proportion. So for this example, let's say that the population proportion is 0.50. This changes the original population value on the right. The default sample size in StatKey is n equals 200. Let's change this. Let's say that we're going to use a sample size of n equals 30. So we have a large population with p equals 0.5, and we're going to take a simple random sample of n equals 30. We'll generate 1 sample to begin. In our first simple random sample, 15 out of 30 had the trait, so p hat equals 0.500. This value is then plotted on our sampling dot plot at the left. Let's take another simple random sample. In our second simple random sample, 19 out of 30 had the trait, so p hat equals 0.633. This value is also plotted on the sampling dot plot. We could continue to do this, and each time our sample proportion is plotted on the dot plot. At the bottom, we can also see this triangle with a gray number. This number right now 0.511, is the mean of this distribution. To speed things up, we can generate a few thousand random samples at a time. I usually tell students to generate at least 5,000 simple random samples in order to get a good picture of the sampling distribution. Here we can see that I've taken 5,006 simple random samples of n equals 30 from a population where p equals 0.5. For each of those samples, the sample proportion was recorded on this dot plot. The mean of this distribution is 0.501. The standard error, which is the standard deviation of the sampling distribution, is 0.091. Let's go back to the StatKey homepage and look at an example involving a quantitative variable. For a quantitative variable, we're going to be constructing a sampling distribution for a mean. Again, StatKey has a number of data sets built in. For this example, let's look at the NFL contracts from 2015. On the right, we can see our original population. The population size is 2,099. If we go to Show Data Table, we can see all 2,099 players' names and their yearly salaries in millions from 2015. The population mean, or mu, is 2.238. The default in StatKey is to take a sample of n equals 10. For the first example, I'll leave it at n equals 10. If I generate one random sample, StatKey takes a simple random sample of n equals 10 from the original population. At the bottom right now, we can see our first simple random sample. Our sample mean is 1.484. In the sampling dot plot on the left, that sample mean is plotted for us. We can take a second simple random sample of n equals 10. This time, we have a sample mean of 2.455. This point is also plotted on our sampling dot plot of the mean. And again, the triangle and the number at the bottom is the current mean of this sampling distribution. Let's take a few random samples. Again, I like to take at least 5,000. Here I have 5,002 simple random samples of n equals 10 from this known population. This is my sampling distribution. It has a mean of 2.249 and a standard error, which is the standard deviation of this distribution, of 0.957. We can see that the original population was strongly skewed to the right. Our sampling distribution is also skewed to the right, though not as strongly as the original population. One thing I want to demonstrate is that when the sample size is larger, the distribution becomes closer to a normal distribution. I also want to show that as the sample size increases, the standard error decreases. So let's change our sample size to n equals 50. We'll generate a few thousand simple random samples of n equals 50 from this known population. The mean of our sampling distribution is 2.238, and the standard error is now much smaller. It's 0.431. We can also see that this distribution is closer to a normal distribution. Later in the course, you'll learn that this phenomenon is known as the central limit theorem. Let's go back to the PowerPoint slides. These are the key takeaways for this learning objective. If we were to repeatedly pull samples of n from a population and record a sample statistic, that distribution of sample statistics is known as the sampling distribution. In StatKey, we're only able to see examples of sampling distributions for means and proportions, but we could follow the same procedure for a difference in means, difference in proportions, correlation, or regression slope. The standard deviation of a sampling distribution is known as the standard error. Sometimes you'll see this abbreviated as SE. As sample size increases, the standard error decreases, and the shape of the sampling distribution becomes close to a normal distribution. Here's our second learning objective: interpret confidence intervals. This is covered in section 3.2 of the Lock 5 textbook. A confidence interval is a range of values which we believe with a given level of confidence contains the population parameter. This is the first inferential procedure that you're learning in this course. Data from a sample are used to estimate a population parameter. This is the general form of a confidence interval that we'll be working with throughout this course. It's the sample statistic, so the sample mean, sample proportion, correlation, or any of the sample statistics that we saw earlier, plus or minus the margin of error. The margin of error is determined by two different factors. First, your level of confidence. This is a normal distribution showing the empirical rule. Recall that 95% of the normal distribution falls within 2 standard deviations of the mean. 99.7% of the normal distribution falls within 3 standard deviations of the mean. In order to be more confident, we need to have more of the normal distribution, which means we're going out more standard deviation units. 2 versus 3 standard deviations is essentially the multiplier, or what we're going to call the multiplier. If you're constructing a 95% confidence interval, you want to go out 2 standard deviations, so the multiplier that you're going to see a lot in this course is 2. The second factor that influences a confidence interval is the standard error. The standard error is the standard deviation of the sampling distribution. So as the standard error is larger, the confidence interval is going to be wider. Similarly, if the standard error is smaller, the confidence interval is going to be more narrow. Let's look at an example. In a sample of 100 Americans, 26 are at least bilingual. So a representative sample of 100 Americans were surveyed and asked, do you speak 2 or more languages? 26 out of 100 said yes. This gives us a sample proportion, or p-hat, of 26 divided by 100, which is 0.26. Later in this video, we'll learn how to use StatKey to construct a bootstrap sampling distribution, which is where we'll get our standard error. Here, I've done it for us. We have a standard error of 0.043. We'll use this information to construct a 95% confidence interval. So we're using data from our sample of 100 to make an inference about the population of all Americans. Our sample statistic was our sample proportion of 0.26 plus or minus 2, because we're constructing a 95% confidence interval, times our standard error of 0.043. First, we compute the margin of error by multiplying 2 times 0.043. Then we subtract and add to find a 95% confidence interval of 0.174 to 0.346. To interpret this confidence interval, I would say that I am 95% confident that in the population of all Americans, the proportion who are at least bilingual is between 0.174 and 0.346. Now let's look at 2 examples of how we can apply this confidence interval. Is there evidence that less than half of all Americans are at least bilingual? If less than half of all Americans are at least bilingual, that means that the population proportion is less than 0.50. Our entire confidence interval is less than 0.50. This means that 0.50 is not a reasonable estimate for the population proportion. So yes, there is evidence that less than half of Americans are at least bilingual. Here's another example. Is there evidence that the proportion of all Americans who are at least bilingual is different from 0.25? 0.25 is contained within our confidence interval. This means that this is a reasonable estimate for the population proportion. No, there is not evidence that the proportion of all Americans who are at least bilingual is different from 0.25. Note that we can't say that the population proportion is 0.25. We can just say that this is a reasonable estimate. So there's not evidence that the population proportion is different from 0.25. Here's our third learning objective. Explain the process of bootstrapping. This is covered in section 3.3 of the Lock 5 textbook. When we looked at the first learning objective, we used StatKey to construct a sampling distribution when the population was known. In most cases, though, the population is not known. In most cases, we only have data from a sample. Bootstrapping is a resampling procedure that uses data from one sample to generate a sampling distribution by taking random samples with replacement from the original sample. This is a method of constructing that sampling distribution when the population is not available. Let's go to StatKey again to look at a few examples. In StatKey, we can see that there's a column for bootstrap confidence intervals. When we bootstrap confidence intervals, we construct a bootstrap sampling distribution that we then use to find the confidence interval. So we can bootstrap sampling distributions and confidence intervals for a mean, median, standard deviation, proportion, difference in means, difference in proportions, slope, or correlation. The first example that I want to look at is a confidence interval for a single proportion. At this point, though, we're just going to be making the sampling distribution. We're not going to be constructing the confidence interval quite yet. In StatKey, again, there are a number of built-in data sets, but for this example, I'd like to use the data that we just worked with in our last example. So I'll edit the data. In our last example, we had a sample of 100 Americans. 26 in that sample were at least bilingual. So I'll enter my sample data here, which changes the original sample on the right. 26 out of 100 in our sample gives us a sample proportion, or p hat, of 0.260. When we're bootstrapping, we are taking a simple random sample from the original sample with replacement. That means that every time an individual or case is randomly selected from the original sample, they're put back into the sample. So it's possible, or it's probable, that an individual can be selected more than once to be in the same bootstrap sample. I'll generate one bootstrap sample. In this first bootstrap sample, 29 out of 100 gives us a bootstrap sample proportion of 0.290. As before, on our dot plot, that bootstrap sample proportion is recorded. In my second bootstrap sample, 22 out of 100 had the trait for a sample proportion of 0.220, which again is plotted on our dot plot. And at the bottom, we have an arrow showing the mean. Like before, I typically recommend that students take at least 5,000 samples. Here I have 5,002 bootstrap samples. And for each bootstrap sample, the proportion is recorded on this dot plot. This dot plot has a mean of 0.259 and a standard error, which is the standard deviation of this distribution, of 0.043. This is our bootstrap sampling distribution for this example. I'm going to go back to the StatKey homepage now to show you an example involving a mean. Here, we'll construct a bootstrap sampling distribution for a single mean. We'll use the first built-in data set here, Mustang prices. On the upper right, we can see our original sample. Our sample size is n equals 25, and our original sample mean is 15.98. If I generate one bootstrap sample, I think it's easier to demonstrate with a quantitative variable how the resampling with replacement works, because we can see here the value of 24.800 shows up 5 times in this bootstrap sample, while up here in the original sample it only appeared once. So this case was selected to be in the bootstrap sample, and then it was thrown back into the original sample when the second case was selected. So it is possible, and it's actually probable, that some cases will be selected more than once and appear more than once in a single bootstrap sample. There are also some observations from the original sample that do not appear in the bootstrap sample. For example, here the value of 45 is in the original sample, does not appear in the bootstrap sample. Our bootstrap sample size is always going to be the same as the original sample size. Here, n equals 25. The mean of this bootstrap sample is 17.54, and that is recorded on the bootstrap dot plot of the mean on the left. We'll generate a few thousand bootstrap samples. Here I have 5,001 bootstrap samples. The mean of this sampling distribution is 16.011. The standard error, which is the standard deviation, is 2.182. Once we have this information, there are 2 different ways that we could construct a confidence interval. So let's go back to the PowerPoint slides to look at those 2 different methods. This is covered in sections 3.3 and 3.4 of the Lock 5 textbook. The first method for constructing a bootstrap confidence interval using StatKey is the standard error method. This is similar to the example that we looked at earlier, where we used this general form of a 95% confidence interval. We took the sample statistic plus or minus 2, because it's a 95% confidence interval, times the standard error. The sample statistic we can get from the original sample, and the standard error we could get from our bootstrap sampling distribution. The second method is the percentile method. Let's start by looking at an example of the standard error method. We'll use the bootstrap sampling distribution that we just constructed for Mustang prices. Our sample statistic is the mean of the original sample, 15.98. Our standard error is the standard deviation of the bootstrap sampling distribution, which is 2.182. We need these 2 values now to construct a 95% confidence interval using the standard error method. So here our sample mean was 15.98, and our standard error, which I'll abbreviate as SE, was 2.182. To construct a 95% confidence interval, we have the sample statistic plus or minus 2 times the standard error. First, we multiply to find the margin of error. 2 times 2.182 equals 4.364. Then we subtract and we add. 15.98 minus 4.364 gives us a lower bound of 11.616. 15.98 plus 24.364 gives us an upper bound of 20.344. Confidence intervals are usually presented in brackets. To interpret this confidence interval, I would say that I am 95% confident that the mean Mustang price in the population is between 11.616 and 20.344. Let's go back to StatKey to see how we could construct this confidence interval using the percentile method. Using the percentile method, after you construct your Bootstrap sampling distribution, select two-tail. All of the confidence intervals that we're going to construct in this course will be two-tailed confidence intervals. The default in StatKey is a 95% confidence interval. Here, our lower bound is 12.032 and our upper bound is 20.536. Let's look at another example. This time, let's construct a confidence interval for the difference in proportions. There are a number of data sets built into StatKey again. We'll use the default. Text messages by age. So here in our original sample, we can see that we're comparing teens to adults in terms of the proportion who say that they use text messages. In our sample of teens, we had 800 teens and 696 said that they do text message for a sample proportion within the teens of 0.870. For adults, we had a sample of 2,252. 1,621 said that they do use text messages for a sample proportion within the adults of 0.720. Let's generate a few thousand Bootstrap samples to get a good picture of the sampling distribution. Then, to get our 95% confidence interval, we'll select two-tail. Our 95% confidence interval for the difference in the proportion of teens and adults who text message is 0.120 to 0.180. Oftentimes when we're looking at the difference in proportion or difference in means, we want to know if there's a difference between the two groups. In order to determine if there's a difference, we look to see if 0 is contained within the confidence interval. 0 is not contained within this confidence interval, so it is not a reasonable estimate for the difference between the two proportions. This means that there is evidence that teens and adults differ in terms of the proportion who use text messages in this population. I want to go back to the PowerPoint slides now to review a few things before moving on to the last learning objective. Earlier, we saw how sample size impacts standard error. Now let's look at the impact of sample size on confidence intervals. As the sample size increases, the standard error decreases. This means that as the sample size increases, the confidence interval becomes narrower. As the sample size decreases, the confidence interval becomes wider. Our last learning objective this week is to construct Bootstrap confidence intervals using Minitab Express. This is not covered in the Lock 5 textbook. Let's go to Minitab Express now to look at a couple examples. I'm on a Mac, so in order to use the bootstrapping procedures in Minitab Express, I could either go to resampling, or I could go to statistics, resampling. If you're on a PC, the bootstrapping and randomization procedures are separate, so there may be an extra step for you. The first example that I want to show you is bootstrapping for one sample proportion. We're going to continue with the example that we saw earlier with Americans who are at least bilingual. I do not have any data in this Minitab Express file, so I am going to use summarized data. There were 26 adults in our sample of 100 who were at least bilingual. Unfortunately, the maximum number of resamples in Minitab Express is 1,000. Remember in StatKey I said that I usually tell students to take at least 5,000 to get a good picture. Unfortunately, Minitab Express will only do out to 1,000 at a time, so we're always going to use the maximum number here of 1,000. Under options, we're not going to change anything this time, but you can see if you were doing a confidence level other than 95%, this is where you could change it. When we click OK, the first thing Minitab Express will give us is a Bootstrap histogram. This is similar to the dot plot that StatKey gives us. In red here, we can see the boundaries for our 95% confidence interval. If we scroll down, we can also see them in the last table. Our 95% confidence interval here is 0.1800 to 0.3500. So I'm 95% confident that in the population of all Americans, between 0.18 and 0.35 are at least bilingual. The next example that I want to show you is going to use data from the online notes. On the page for bootstrapping in Minitab Express, I'll run through this example using the class survey data set. Here it looks like we want to construct a 95% bootstrap confidence interval for the mean GPA. I'll go to Statistics, Resampling, Bootstrapping for one sample mean. The variable that we're interested in is GPA. Again, under Options, we're not going to change anything. But if you wanted a confidence level other than 95, this is where you would change that. The output for one sample mean is going to look similar to that from one sample proportion. We have our Bootstrap histogram, which is similar to the dot plot that StatKey gives us. Our 95% confidence interval for the population mean is 3.16496 to 3.29735. To interpret this confidence interval, I would say that I am 95% confident that the mean GPA in the population from which these data were drawn is between 3.16496 and 3.29735. Let's walk through one last example. We have data concerning biological sex, so let's compare the mean GPAs of females and males. Statistics, resampling, and now we have two means because we're going to be comparing the mean for females versus the mean for males. Samples is our dependent variable, or the quantitative variable that we're comparing, which is GPA. Sample IDs are two groups, our females and males, which are in column 2, biological sex. We click OK. Again, we get a Bootstrap histogram, this time for the differences in means. If we scroll down, we can see that we're comparing females minus males. Our 95% confidence interval for the difference is negative 0.08699 to 0.18988. So I'm 95% confident that in the population, if we would take the mean GPA of females minus the mean GPA of males, that difference would be somewhere between negative 0.08699 and positive 0.18988. Note that this confidence interval does contain 0. So 0 is a reasonable estimate for the difference in GPAs in the population. In other words, there's not evidence that females and males differ in terms of their GPAs in this population. This is the last example that I wanted to cover, but very quickly, let's review the learning objectives from this lesson. Learning objective 1 was to construct and interpret a sampling distribution using StatKey. Learning objective 2, interpret confidence intervals. Objective 3, explain the process of bootstrapping. Objective 4, construct bootstrap confidence intervals using StatKey. And Objective 5, construct bootstrap confidence intervals using Minitab Express. If you haven't done so already, I recommend that you at least skim through the online notes and read through the Lock 5 textbook chapter this week. If you have any questions as you're working through those materials, working on your Wiley Plus homework assignment or the lab assignment, you should post your questions to the Canvas discussion boards.